All right, so AP Calculus, AB. Today's date is Tuesday, March 10th, 2020. We're talking about the area between two curves, which was touched on yesterday, and I need to fix that. I did too much hard stuff yesterday. Remember where we had a curve on top, a curve beneath, and we subtracted the two? It's the same lesson now, so sorry. So let's talk about our objective today. Stego, go for it.
Find the area between two curves that might intersect each other more than twice.
Yeah, so that objective was based off of yesterday's objective, which is not quite correct. So there's tiny mistakes occurring here. I will get those tweaked for next year. But yeah, you can have curves that intersect each other like 17 times. And how do you find the area? Because you might say, the area is 0. That's because the positive and negative areas are canceling each other out. And you have to divide them into multiple different segments. And I don't do a good job explaining that in these notes, but I do have, I think, at least one problem on the homework that does that. So, water tank problem. We've seen this guy before. Who wants to read? Yes, Claire, thank you.
Water enters the tank at a rate of 3 gallons per hour and leaves at a rate of t squared minus 6t plus 11 gallons per hour. What is the total change in water from time equals 2 to time equals 4?
Yeah, doesn't that sound familiar?
Very.
Yeah, it's start plus change equals end type of thing, right? And if we had an entering and leaving, we always do entering minus leaving immediately, right? Let's go ahead and approximate the graphs of these things. So t squared minus 6t plus 11. What does that look like? I guess I could just graph that, right? And then copy paste it and you guys can follow along. So if I go to desmos.com, what does that look like? Because it doesn't factor since 11 is prime. So t squared minus 6t, start graphing. It's going to look like this. I'll have 6t, or I'll do 6x to the power of 2 because it doesn't like t. X squared minus 6t. X squared minus 6x plus 11. It looks like that. And my scale is from 0 to 5, so let's make this look nice. Projector mode, go from 0 to 5.5 and make my y-axis go from 0 to, 6. All right, so that's what our graph looks like, and we don't want minor grid lines. And I'll zoom out just a tad. Okay, so there's our graph. And zoom. Hold on, can I change my step by 1 so it looks nicer? Okay. There is our graph. And you guys don't have the technology to do this, but that's what it looks like. So go ahead and approximate the sketch of that graph. And I'll maybe make this a little bit wider. So it has points here at 3, 2. It looks like 2, 3, 4, 3, and also over here at 1, 6, and 5, 6. So if you had to make the points, there they are. So that is that the entering or the leaving function? That's the leaving function. So let's label that L of t. Capital L of t. And what about the entering function? How do we graph that?
It's like a straight line, right?
Straight line through where?
The y-axis.
Y-axis at 3, 2, 5,
3.
3. Okay, 3. And I'll drag that down. Okay, cool. So we have the entering function, we have the leaving function. Let's go ahead and label that blue line E of t, capital E of t, for the entering. And I'm looking for the total change in water between 2 and 4. And hey, that makes sense because between 2 and 4, it's only at one spot. So I don't have to worry about adding and subtracting different segments. If I had, for example, what is the total change in water, and I change this 2 to a 1, then I'd have a positive area and then I'd have a negative area, or vice versa, depending on which one I'm doing. And I'd have to split this up into 2 different integrals. That's as easy as you make it. So if you ever have an intersection with an entering and leaving function, create as many integrals as you need whenever there's an intersection. So that one would have 2. If I did even another one, I'd have to have 3 integrals. But this one is nice and easy. There's only one integral that I need, and it's between 2 and 4. So what is that integral in general? What is the integral when I have an entering and leaving function? So yeah, integral from a to b of
F of t minus t, or L of t minus, wait, no, e of t T minus L of T.
There it is. So I'll do that in black and I say E of t minus L of t. And then all that thing dt. So that's our general formula that we're always going to be using. And in this case, I'm going to come down here and actually fill in what's happening. So I have the integral from 2 to 4, as Gio said. And I'm going to, I think we should probably fill in the numbers here. So our E of t is 3, right? So I'll say our E of t is 3. And then that's going to be subtracting. And I have to do parentheses for all of our L of t unless I want to distribute the negative right now. Subtracting t squared minus 6t plus 11. And then all that thing in parentheses dt. Make that dt look a little bit nicer. All right, now let's do this by hand. You will be expected to do these by hand if they're easy like this, and if they're hard, then you have a calculator. So let's try this by hand to get some practice in. First, let's combine like terms. So I'm going to rewrite this integral. This is now the integral from 2 to 4 of what?
T squared.
Negative t squared, and yeah, negative 8 over here. And plus 6t, and then all that thing dt. Okay, so we've simplified it. Now let's go ahead and take the antiderivative. I don't know, how much room do I have down here? I'm going to maybe take the antiderivative on this next line over here. Antiderivative, go. Someone. Yes, arrow. Perfect.
Interesting. Is it, so you divide down first, right?
Yep, so,
Yes,
or
so-
sorry, add 1 and then divide down. Divide down second.
Divide down second. So negative t divided by 3 to the third?
There it is.
Okay.
Keep going.
Plus 3t to the second.
3t to the second, because we divided down by 2, and 6 divided by 2 is 3. Keep going.
Minus 8t.
8t. And to finish this off, to make it official, is it plus c or evaluation bar?
Valuation bar.
From
From 2 to 4.
2 to 4. All right, perfect. Thank you, Arrow. Got our good review in here. And then now let's start plugging in things. Let's plug in the 4 first, and then we'll subtract when we plug in the 2. So I'm just going to rewrite it with that 4 plugged in. So I have that negative 4 to the power of 3, all divided by 3, plus 3, and that's 4 now to the power of 2, minus 8 times 4. And then I'm going to subtract when I plug in the other thing. So I'll switch back to blue here, I guess. I don't want to do red and green because I mix those up all the time. This is going to be subtracting, and I have a negative. Okay, this subtracting should really have a parenthesis because I'm subtracting this entire quantity. So I have a negative, t is now 2. So negative 2 to the power of 3 all over 3 plus 3, and then t is again 2 to the power of 2 minus 8 times 2. Be careful with your negatives. Negatives will mess you up a lot. Put parentheses around things. So far, so good? Okay, now another volunteer to supply. I haven't heard from Stego very much. Go for it, Stego.
It's going to do negative 4 to the power of 3. That's negative 64 divided by 3.
Yep, keep going.
Plus 16 times 3. That's 48.
Yep,
And then minus 32.
perfect. Keep going with the blue.
Minus negative 4.
Careful. 2 to the power of 3 is,
Oh, 8.
yep, so negative 8/3. Keep going.
Plus 12 minus 16.
There it is, nice, okay. Gio, keep simplifying, please. Let's distribute the negative right now, Gio, before you make a mistake.
Okay,
So,
so that's going to be positive negative 12, and then positive 16.
perfect. All right, let's get those things with 3 in their denominators dealt with first, because maybe the denominators will go away. Bless you.
Thank you.
Bless you, sorry. So,
Delayed reaction.
so how did I do that?
What is a positive 8 minus 64?
What's positive 8 minus 64?
Yes, or negative 64 plus 8.
Alright, negative 50, wait, 50, 56. Oh yeah, 56.
And class, is 56 divisible by 3?
Probably.
How can you tell?
It's 6. What's 6? It's a multiple.
So the trick with 3s is you add the numbers together. 5 plus 6. That is 11 divisible by 3? Then 56 is not divisible by 3. So let me ask you this. Is 1,967 divisible by 3?
Probably.
Claire.
Wait.
No.
Add them
Yes,
together.
Yes, it
Yes.
is.
No, it's
21.
not.
No.
Isn't it
What?
23?
Isn't it 21?
It's 23.
Well,
Yeah.
here's an even bigger trick. Since 9 is divisible by 3, ignore it. That's already divisible by 3.
Oh, so then you
Well-
can ignore the 6 too?
Ignore the 6 as well.
So then it's
1 plus 7 is
8.
Oh, yeah.
8, and 8 is not divisible by 3, so 1,967 is not divisible by 3. Cool little tricks there. Coming back here.
So could you just keep on doing that, like, and then you get 23 when you add all of them, and then 2 plus 3 is 5, 5 is
Yeah, you can do it over and over again. Yeah, it boils down. It's really nice. So keep going, Gio.
So that would be
These two,
16.
and then let's do these two.
That's 28.
Ooh, careful. I have a negative 12 and a positive 16.
Oh, 4.
4, and then 4 and 16.
20.
We should probably make that into one fraction. So let's multiply the top and bottom here by 3. And then Gio, what's our new expression? It's negative 56 thirds plus
20. Oh wait, 60.
60 thirds, and our final answer is
I don't know. 4. Wait.
4 thirds. Yeah,
So you add all those. Every two. Oh wait, okay.
I just added the numerators. 56, negative 56, and 60 is 4.
Okay.
Nice. All right, and what are our units here? We should be careful. I didn't ask for units. I didn't ask for anything. There's no question, really. Well, I guess it is. What is the total change in water? So if the, yeah, so what should our units be? Why is it gallons? You're correct, but why?
Because Art's asking how much it changed in gallons. It's in gallons.
What is the total change in water? It doesn't say in gallons in the problem, in terms of this question right here.
Wait, but yeah, the integral of
Because
the
it makes sense.
gallons per hour.
Say it louder, Arrow.
You took the integral of the gallons per hour.
Yeah, so we are taking an integral right here, and we're taking integral of these functions. These functions were given in gallons per hour. Whenever you take an integral, get rid of a time unit. If it was gallons per hour squared, you get rid of the squared. If it was gallons per hour, get rid of an hour. If it was gallons, then weird things are happening, and that's a bad problem. If I take the derivative, I add on a time unit. So if I took the derivative, I'd add on a square. But I'm taking an integral, I'm going backwards, so I'm getting rid of a time unit. That's why it's in 4 thirds gallons. All right. So, and then you've already learned this rule, but let's say it again. In general, if I have, I can also call this the top and the bottom. If I want to find this area here, and I like making them kind of like rectangles, because you're really having a bunch of rectangles. What are the two formulas? Give me a formula with f of x and g of x. Give me a formula with top and bottom. And let's say, yeah, we have the integral from a to b. Integral from a to b of something, and then give me a second formula, integral from a to b of something. Give me a formula with f of x and g of x. Give me a formula with top and bottom. Go for it, Arrow. Give me one of them.
The integral from a to b of top minus bottom.
Perfect. Top minus bottom. And then all of that dx, or d, whatever it was.
Right.
Actually, I'm going to just leave it like that. This one, I'm going to be a little bit more formal about it. Gio, give me one with f of x and g of x.
This is the integral between a and b of f of
this. Yeah, there it is. And not dt, but
Yeah.
Yes.
yeah.
Same thing.
Yeah, either of those. Always top minus bottom. And again, I want to put a giant note here. Let me type it and maybe make the font size small so I can fit it in here. Have as many integrals as there are sections. And I'll put sections in quotes. Because if I have a bunch of different sections, I will need a bunch of different integrals. And I said that up above, and I don't have the best example here, but if I had this guy where I had these areas, I would have this area, and this area, so I'd need 3 integrals for 3 of these different sections. So every time you have an intersection point, you need to have a different integral. So be wary of that. All right, that concludes the notes. I'm guessing your fist of 5 is probably going to be a 4 or 5 since you already had time to practice 11-1, which I should check, by the way, after I do this. So give me a fist of 5 on how well you can find the area between 2 curves that might intersect each other more than twice. I see with and without, I guess. I see a 4. I'm writing down 3, a 4, and a 4. Thank you.